In this video, I want to show you how to set up a groundwater model of a glacial outwash sand aquifer. And for this model, we're going to take an example from a glacial outwash in Wisconsin. And in particular, we're going to look near the town of Waupaca, Wisconsin, which is shown here in the red dot. And the map here on the left, actually all of these images that I'm showing here are from the USGS Groundwater Atlas, which is available at this website. It's a great resource for information about aquifers of the US. So this is the Fox-Wolf River aquifer system, and you can see this green band is Outwash, and to the east, this area is covered by glacial lake deposits and ground moraines. This area right here is near Waupaca. And in order to set up the model, we need to know a little bit about what the aquifer there is like. Well, we know what glacial outwash aquifers are like. It's very rich in sand, and it's quite permeable sand. In general, that would be the expectation. And we can go to the Groundwater Atlas and get information about the thickness, and we can get information that we can use to estimate the recharge, both of which we'll need to set up the model. This map here, which is the thickness, and you can see that there are 3 zones here of aquifer thickness, and near Waupaca, the thickness is given here as it's less than 100 feet thick. So what I'm going to do to start off this model is just take this information, and it's pretty general, but I'm going to assume that the thickness here is less than 100 feet. So I'll assume it's 90 feet or 30 meters thick. Actually, 30 meters is probably more like 100 feet. But that ballpark. And I'll assume that the recharge is 0.5 feet per year. So we'll take this as a rough estimate of the average recharge. And we'll convert that into meters. So we'll start with this value. We could get a better estimate of what the recharge was if we took a hydrograph analysis, these individual points. And we'll do that later on in the course, but for now we'll just use this as a starting point. So I started up GMS, and I went to online maps, and I added an online map, and I navigated to Waupaca, Wisconsin. So there's Waupaca. And then I wanted to determine the area that I would use for the model. So there's a stream here that connects up these lakes. So that would be a good feature to have at the southern end of the model. And then I went up here, and there's another stream here. It's a little bit hard, a little bit faint on this map, but that looked like a good place to have as an upper boundary. And then I would be focusing my model really on this area right in between those 2 streams. So what I did was to navigate using the street map to Waupaca and identify the area. And then I went and exported this map and made a TIFF. And this is the TIFF that I made. And I did that because if I kept the world street map on, then it would be constantly wanting to update and go out and get additional information. And that's a great feature to have, to be able to bring in these data, but it's kind of slow and cumbersome if it's constantly doing that. So I just copied the map that I wanted to use, and then I'll use this one instead. And then once I identified this frame, I went and did the same thing for the elevation data. I went and downloaded the elevation data from online maps and then copied it and made this file that is the elevation data. And I did the same thing with the air photo. I downloaded that, or I went and used online maps to bring in world imagery, and then I copied it to this file. So I have all of these 3 different kinds of images that I can use, and as well as the data in this file that I can use to generate other files. So you can see here the stream valleys, and then these linear ridges here in this glacial terrain. Okay, so another thing that I did actually is to go, and if I go up here to the bar, the menu bar, and right click and go to annotations, then I get a bar here that I can use to put some annotations. Well, it went up here into the menu on the map. So I can put some text, and I can put a north arrow, and in this case I put a scale here, and that includes this feature in the Model Explorer. And so this is a scale bar that then I can add to all of the maps that I generate as part of the modeling process. Okay, so I'm going to want to use this elevation data to set up the boundary conditions for this model. So to do that, I'm going to select this file here and right click, and I want to generate 2D scatter points. So I select that, and that generates the scatter points. I've already done that with these guys here, so it generates another set of points, and then I select those points and create a 10. So I'll convert to a 10. Now, what I did initially, when I first did this, it gave me the ability to set the grid size, and the default cell size was a few meters, and I set it to 20 meters because you can see this is 3 kilometers, so this is about 10 kilometers or so on a side, and we don't need cells really small, so we don't need them at the finest resolution. So I set it to 20 meter cell size, and that means that this file, this 2D scatter set of the elevations, and this TIN file are smaller than they would otherwise be. So I'd recommend doing that. When I first did it, I didn't do that, and these files were quite big and took longer time to load. Okay, so converted to a 10, and let's take a look at that 10. So when this is the topographic surface as a 10, where I've adjusted the display a little bit. So if you go here to display and display options and go to 10, then you can select here the contours, what the line thickness is, what the contour interval is, and that may help have it show up a little bit better. I think also these may be selected as default, in which case it'll be probably hard to understand what the 10 is showing you. So I would unselect them and just show these topographic contours. Okay, so we're going to need this 10. These scatter points, we won't really need them again. We can keep them here or we can delete them. I'm going to delete this one because it's a duplicate. And we could just delete this if we wanted to make the file a little more compact. Okay, so here is a nice high-resolution depiction of the topography as a digital elevation map. Now I want to set up the groundwater model. Oh, actually, one thing, let's just check this. So if you select the tin and go to Properties, well, let's open the tin and yeah, okay. So if you open the tin, this is there can be multiple tins, and let's select this tin. And when you first make this, it's probably just called tin 1. I changed the name so that I could be a little more clear about what I was looking at. So there's topography, and if we right-click there and go to Properties, Horizon ID, the default is 0, but you should change it to 1. That'll avoid some confusion later on. Okay, so now we go to the conceptual model, and let's open this up. And these are the basic components of the conceptual model. This is the map area. So this is what I'm defining, using to define R and K. So I'll give up to 10 layers and defining the conductivity and the recharge. And let me show you what I have here. So the recharge, we went with 5 times 10 to the minus 9 based on that data that we had. And then this is the horizontal hydraulic conductivity, 10 to the minus 4 meters per second, and a 10-to-1 vertical horizontal ratio. This is a starting point, but it'll turn out this would be in the right vicinity for calibration. Okay, so then the stream. So we've got a stream up here and a stream down here. And you can see that green line, a little hard to see, but that's the trace of the stream. And you can see that with this tin data is really quite high resolution. And so you can see when I trace this stream, this is the trace, that I have these vertices here following the stream, but in between it kind of comes out of the stream. So I could probably go in here and digitize the location of this stream a little bit more precisely and have it follow the topography a little more accurately. But what I did was to put in this arc, and yeah, you can see there I got outside of the stream. One of the things that happens is that you can digitize this using different approaches. The tin is one set of data, but you can, if you take a look, say, at the world street map, the stream is also on that. And so I might have used the world street map to get started on this. But what I would recommend doing is that when you put this in, you use the tin to get it in the right spot. So I would probably move that there into the center of the stream, because what we're going to do to set up the stream, let me show you how we have it set up. We click layer range, and we're going to have the stream set up as a drain. And then if we go to the attribute table, there are all the drains. We'll use a conductance of 100 meters squared, meters per second. And we got to make sure to use this feature where we auto assign the boundary condition to one cell. That's going to be important. And then another important aspect, if we go back to the attribute table, is let's go to the nodes. The nodes will be how we determine the elevations of the drain or the elevations of the stream. And we're going to tie those elevations to the tin. So we can do that by, I've got to click the right one, that little arrow there, go to tin, and then we select the tin that we want to use. And now all of the nodes on the streams are tied into the elevation in the tin. So there are also some lakes here. There's a lake there, and there are a couple smaller lakes here. So I made those specified heads, some constant head right there. Also used layer range, and then set up the attributes much like I did with the drains, where all of the arcs are set as specified heads, auto-assign boundary conditions to one cell, and then the nodes select the elevations based on tins. Now, we should probably check and make sure this is working right. These lakes we're going to assume are all at the same stage, and hopefully the tin gives us that result. But if not, sometimes the edges come up a little bit. We could go in and override this and simply determine what the elevation of that stream or that lake was, and include that instead of using the tin. This is how we'll set it up at first. And then we're going to use a grid. We're going to use a U-grid on this. And so I went in and set up a U-grid coverage that will allow me to specify the size of the grid. So I can, let's see, I select the external. There we go. So along the outside, the average spacing is 500 meters. And then I also did the refinement along these streams and along the lakes. Okay, so then I use that to generate the grid. And the way I set this up was to go map to U-grid. And then I initially set it up using a 2D grid with Voronoi polygons. So I did that and created that U-grid. And that one is here. Okay, so there's the 2D Voronoi polygon. I'll turn that off. So there it is. And now we need a 3D grid. So the way we're going to do it is to utilize this tin of the topography and make the upper surface of this Voronoi polygon grid the topography. So we'll do that by clicking on this tin data, and that gives us the tin menu selection right here. And we'll go horizons to U-grid. And on this first menu, or first page here, we're going to select use horizon tins, and then go next. And we have a variety of U-grids, but we need to pick the 2D U-grid. This will probably be the first one you make, so it's that one. And then the top elevation is going to be select tin elevations and select the tin that has topography. And then the constant, then the bottom is the bottom of the model. So what I did was to say, well, this aquifer is about 30 meters thick, and the elevation is 235 to 250 or so meters. So I'm going to just say the bottom elevation is a constant 205 meters. And then this next page allows you to select some specifics on the interpolation method, the nodal function, and the meshing function, or meshing option. So one thing I'd recommend that you do is check this for the minimum element thickness as 2 meters. So that'll avoid having really super thin elements. And these guys can just stay at the defaults. And so we hit finish. And that'll generate a U-grid. And that's shown right here. I have several U-grids in this model already, but this will be a single layer U-grid that has the upper surface as the topography. So there it is. There's the 2D, and then you can see the three-dimensional effect. You see these topographic features from this glacial landscape. Okay, so there's our model. Right now it's just one layer thick. So what we can do is go to the U-grid selection there and select the select cells, select all of these guys, right click and split the layer. So if we do that, we get another U-grid, and let's turn that one off, turn the first one off, and we can see that this now has 2 layers in it. Okay, so I did that a few times, and this is, I think, a good pointer here where so we've done it now twice. Now I want to split that upper layer in 2. So I click this guy, select single layer, and then layer 1, I can select the upper layer and split that. That gives us another U-grid. And then I'm going to go here. Now we've got the layers 1 and 2 are the original layer 1 split. So I want to go to layer 3 and select them, split that, and that should give us 4 layers. Let's take a look. There you go. Kind of hard to see, but it gets kind of complicated looking, but there are the 4 layers. Okay, so I did that, and these grids here are the grids that I generated when I did that, and I ended up with this grid here. Take a look at. Let's turn off these grids and go up here, take a look at this one. So there are the 4 layers. Here are the results of the model in plan view, where I've turned on the underlying base map so we can see where these contours are relative to the underlying, or relative to the features at the actual site. In this view, I think that the Voronoi polygons are getting in the way, so I'm going to turn those off. So you can see the underlying roads, I think, and there are a lot of mod flow symbols here. The blue triangles here are flooded cells, and you can see there are quite a few of them. There are some along the stream here and along this stream. This is indicating that the groundwater table, the hydraulic head, is above the upper surface, and we can check here, we're on layer 1. So that would indicate that the hydraulic head is a bit too high in this model. But you can see that there are also some dry cells here, They show up as red triangles in areas where the hydraulic head is not plotted, where it's just blank. We can also take a look at this particular little pond here and how it fits in the overall hydraulic head contours. So our groundwater flow is going like this, perpendicular to these contours, and the head contours hardly change at all as they go past this pond. So that indicates that this pond is a flow-through pond, and the groundwater comes in and enters the pond on the upstream side and flows out on the downstream side. So that's reasonable. That's the kind of pond that we would expect to be in a landscape here. This lake over here is also gaining. This hydraulic head here is higher than the head of the pond, so we have water flowing into this pond from these sides, and this head right here is also just a little bit higher than the hydraulic head in the pond. We can check that by going to this U-Grid menu selection and select cells, and then we can click on that cell and see that it's 246, and click right here outside, and it's 246.8. So the head along this part is a bit higher than the head in the stream. So that all seems good. One aspect that is a little bit unusual here and unexpected are these closed contours along the stream. You can see them there along the stream to the north, and they're also here along this stream. And the reason for that is because when I initially put in the boundary condition representing this stream, I was not quite as precise as I could have been. So I'm going to make the hydraulic head transparent and turn on the 10 representing topography. And you can see that this is the boundary condition representing the stream, this green line. And you can see in places it's right along the axis of the low part in the contour representing the stream, but in other places it's not, it's off. And as a result of that, the elevation of the bottom of this drain representing the stream is going to rise and fall instead of just sloping continuously as it would if it was along the base of this, really along the axis of the stream. The model could be refined a little bit by locating the stream a little bit more accurately. Okay, so I think this model looks pretty good as a first start, but it does seem like with all these flooded cells here, like the heads are a bit higher. So what I'm going to do is run this model again and copy the grid and set up another mod flow, and then change the coverage here to increase the hydraulic connectivity. And that was done because I wanted to drop down the hydraulic heads. So before I did that, I renamed this set of simulations U-Grid K1e to the -4 because the hydraulic conductivity was 10 to the -4 meters per second. And then I set up another simulation where I changed the coverage and set K to 2 times 10 to the -4. And that's shown here. Set up another mod flow, reran it, and then this file with heads is associated with this run where it's K2e to the -4. And keep in mind, I labeled this manually, so that won't happen automatically. You need to make sure to do that if you want to have that labeled. So turn this on, and now this is the hydraulic heads also in layer 1. And let me see, I think, yeah, we need to make sure to turn this off. So we're just looking at the one set of contours. And here's the hydraulic heads now for this setup. And you can see that a lot of those flooded cells that we had in the previous model are now gone. We have some dry cells, but the head is dropped down as a result of doubling the hydraulic conductivity. So that seems reasonable. There are a few small places of flooded cells, bands like this, we might want to take a look at the air photo and see if maybe there's a swampy area there, or maybe there is actually a stream. Another area of interest is this small pond right here. In the previous model, we saw that the small pond was a flow-through pond, but now the hydraulic head in this pond is a bit higher than the head around it. So this pond is actually now a recharge pond, and it's providing water to the groundwater. And so this is certainly possible, but in order to have something like this occurring naturally, you'd have to have a lot of rainfall and interflow recharging this pond and holding the water level high. And so that's possible, but probably more likely is that we would just need to do a little more refinement in the calibration so that this is actually a flow-through pond. So in general, I think we've got a model here that's a pretty good starting point for calibration using site data. Keep in mind that what we've done so far is really just get the topography from the DM and get recharge from a regional assessment. The recharge was actually based on stream flow, so it may be a little bit low, but this provides just a simple way to get started with a groundwater model that would be a starting point for further refinement once we can get access to field data.